Hello students, welcome to the session. In this session, we are starting a new module that is Essential Python Libraries. In this module, we'll cover some basic Python libraries that are required for data science projects. The first library that we are going to cover is NumPy. Since it's not possible to complete the entire implementation of NumPy in just one lecture, we'll be dividing this lecture into two parts. Now let's set the agenda for the first part of NumPy. So in this session, we'll cover the introduction to NumPy. We'll talk about what NumPy is, why we use it in the first place. We'll try to compare NumPy with list and see what kind of efficiency improvements we can do with NumPy. We'll try to perform the same operations that we can perform with list, and we'll see if NumPy is more efficient compared to list. Then we'll talk about the different ways of creating NumPy arrays. Right? We'll talk about how we can create NumPy array using an object, using the range, and using specific values. Then finally, we'll talk about some operations that we can do over NumPy arrays, like how we can use indexing, slicing, how we can reshape our NumPy array, and how we can transpose our NumPy array. So without further delay, let's dive into the lecture. So let's first understand what is NumPy. NumPy is a library and it is a short form for numerical Python. So NumPy stands for numerical Python, and as the name suggests, it provides us various functionalities to perform operations on numerical data, right? Now, one more important concept that we need to understand before we dive into the NumPy implementation, that is ND arrays. Now, ND arrays are nothing but n-dimensional arrays where n represents the number of dimensions in our array. Now, previously we have seen 1 or 2 dimensional arrays or list, we can say like this. This here is a one-dimensional list, right? 1D list, which contains integer values, right? I can have something like this as well, where 1, 2, 3, 4. Now this represents a 2D list of integers. We can see that there is a list, 1D list here, 1D list here as well. Together, they are consolidated into another outer list. We can say this is a 2D list of integers. Similarly, I can have 3D list as well, which will look something like this. Right? Here we can see that there is a 1D list here, 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 and here. These are all 1D list. And this right here is representing a 2D list. This is again a 2D list inside. And together they are consolidated into one outer list, which is a 3D list. So this represents a 3D list of integers. Similarly, we can have 4D, 5D list based on our use case. So n-dimensional array, where n represents the number of dimensions in an array, and array is a list of numbers, right? Now, before we learn what NumPy can do, let's first understand why do we require NumPy in the first place. All the numeric operations that we can do on our numeric data can also be done with a list, right? Then why do we require a NumPy array? Let's discuss this in detail. Now, let's discuss about some of the advantages of using NumPy arrays over list. So one major advantage that NumPy provides us is the speed of execution. The code written in NumPy is going to be much more faster than compared to Python list. This is because NumPy uses C language at its core, which is much faster in executing codes. Another advantage is the efficiency. So in terms of efficiency as well, NumPy requires much less space to perform same set of operations when compared to list. And finally, and this is a standout feature of NumPy, it provides many inbuilt functions to perform operations on our data and to transform our data, which helps a lot to make our code more understandable and efficient. Now let's move on to the hands-on implementation of NumPy. So for implementing NumPy, we'll be using Google Colab in this session. Let's understand what Google Colab is. So Google Colab is nothing but an online notebook, you can say, that can be used to execute Python code on a cloud interface. We can create a new Colab notebook by just writing colab.new, and it will open up a new notebook for us. Now this Colab notebooks has two types of cells. One is text cell, which can be used to write markdown and provide categories or to section our code in multiple parts. So I can write hello world here. And if I run this cell, this will become one category, and whatever cells are below this particular category will be part of this one. I can just disclose this like this. And these code cells, I can just write the Python code in them. And when I click on run, this will run my Python code and give the output just below the cell. So here is my output of the above code. Now let's do the hands-on implementation of NumPy. I have already made a Colab notebook for this. So we'll be using this notebook for our lecture. So as we discussed, NumPy is a short for numerical Python. It is a foundational package for numerical computing in Python, and it provides an ND array object, which is an efficient multi-dimensional array, right? And it provides a lot of functions as well. Now to import this library, we'll just do import NumPy, which is the name of our library, as NP, which will be the alias of our library. We can just run this cell and it will import our NumPy library. Now, as we have already discussed that NumPy is much more faster compared to list, right? Let's see that with a practical example. So let's say I want to calculate the squares of each element in an array. Let's do the implementation using list. So I can just initialize a list called array list, and it could be I for So what this code will do is it will initialize a array list with numbers from 1 to 1000 with an increment of 1, right? This is a list of 1000 integers. So let's just check that as well. Array list. Let's just check the first few elements of this list. Let's just check first 10 elements. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Now I want to square each element. So what I'll do is square array, and I'll do the square for each element in for x in array list, right? So what this code will do is it will take every x value, every element from our array, and it will square that element and store the result in square array, right? Let's check the first few elements of this array as well. First 10 elements. Okay, first we need to run this. Then we can check the first 10 elements, which are 1, 4, 9, which are squares of these numbers, right? So our code is working. Let's see how much time this operation takes while using the list. So I can just have, I need to import one more library, which will be time, import time. And using this library, we can just get the current time so that we can compare how much time it took to execute our code. Now I'll have a counter here, which will be my start time. And I can use time dot time to get the current time. This is the time before doing the square operation. And similarly, we can have end time as well. After this particular line of code is executed, end time will be stored in time dot time. Okay. So I have the start time and the end time for this particular operation. I'll also print this time as well. Print this time taken using list. And that will be end time minus start time. This will return me the time taken in terms of seconds. So let's just rerun this cell. We have first 10 elements like this, and then let's calculate the time required for executing this code. Now we can see this is very small time. If we execute in terms of second, it's not even 1 second, right? So this is very small amount of time that is required to perform this operation, which is because our array size is also very small. We only have 1000 elements. What if I had 1 million elements? It will look something like this. And if I run the same code for this particular list, now the time is much more compared to the previous one. It's around 337 milliseconds. Let's see the time for 10 million elements in an array. If I run this code, here itself it's taking some time to initialize this array. And we can check first 10 elements, it's the same. And now if we calculate the time required to perform this operation, it is 4.3 seconds, right? As we go further, as our data size increases, the amount of time to complete this particular operation will also increase, right? This is why we use NumPy arrays to perform this operation. Let's do the same operation using NumPy. Let's just validate our square array is having squares of all the numbers in our initial array. Now let's do the same operation using NumPy. So in NumPy, I can initialize an array. Let's initialize a NumPy array like this. NumPy array with the same elements. So I can write np.range. My starting index will be 1. And I want 10 million elements. And my increment is going to be 1. Now I'll explain what arrange function does as we go further in the session. But for now, just have a clear understanding that this is the same operation we are doing with this code as well. I'm initializing an array which will have elements from 1 to 10 million. 1 to 10 million minus 1. So we'll go to the end index minus 1, right? So this will initialize my NumPy array. Let's run this. Let's add some cells here. And let's check what my array represents. I can use the same slicing that I use with list as well. It can be directly used with NumPy array as well. I can get the first 10 elements by using colon 10, which will give me first 10 elements. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, let's do the square of all the numbers and then check how much time it took using NumPy arrays. So my middle part is going to be different, but the main part will be same. Just paste it here. And to perform the square in NumPy, it's quite easy compared to list. We can just directly write. We can write square NumPy, which will be our square element array, and we can do array NumPy double asterisk 2. So this represents I took a NumPy array and I'm doing the power 2, which will do element wise square for each element in the NumPy array. Now let's print the time for this as well. Print time taken using NumPy. So we saw while we were working with list, it took around 4.3 seconds to perform this operation. But if you work with NumPy, it will take and time minus start time. Let's run this code. So using NumPy, we were able to perform the same operation in 0.2 seconds, which is a significant difference compared to the list, right? Hence, we can say that the operations performed by NumPy are extremely fast compared to that of list. As we deal with large amounts of data, the operations performed by list will take a lot of time to execute, while NumPy can do the same operations in much less amount of time. Now, let's see how we can create ND arrays using NumPy. So far, we have talked about the difference between NumPy and list. We have also seen how they process the same task in different times. We saw that NumPy performs the same type of task with much more efficiency, right? Now, let's discuss about the different ways of creating ND arrays. So let's just close this so we have more space. Yeah. So first way of creating ND arrays could be we can provide a list as the input, and we can use np.array function will provide list as the input, and this will return a NumPy array. So A1 here is a NumPy array. We can also check the type of A1, which gives numpy.nd array, right? We can also create NumPy arrays using a set. Let's just see that as well. So this set 1, 2, 3, 4, 5 is also converted into a NumPy array. We can also create NumPy array with a given range. So we have used range function before, right? It will start from the start value, which is 1 here, and it will go till end minus 1 value, which is 11 minus 1, 10, right? So I want an array of numbers from 1 to 10. So this will also give a NumPy array with numbers from 1 to 10, right? Now we can use a1.shape to understand the number of elements that are present in our NumPy array. So here my A1 has 10 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So it tells 10 comma nothing. Since it is a 1D array, we have 10 comma nothing. If it is a 2D array or 3D array, we'll have all the dimensions comma separated values. Now we can also do a1.dtype, which will tell us the type of data present in our NumPy array. So here it tells a NumPy array is of integer type elements. And we can do ndim, which tells us about the number of dimensions in our NumPy array. Since this array is a 1D array, it is returning 1. If it was a 2D array, it will return 2, and so on. Now let's take an example of a 2D array. So we can provide a 2D list as an input to np.array function, and it will return a 2D numpy array. Right? We can again check the shape. Here we got 2 comma 3 because this numpy array has 2 dimensions where we have 2 rows and 3 columns. Right? We can check with ndim as well. It will give us the number of dimensions, which is 2. Now let's create a 3D list. Now create numpy array from a 3D list. This we can see is a 3D list and it has returned this array. Let's validate. The shape of this array is 2 comma 2 comma 2, which represents 3 dimensions. We can confirm using a1.dim and dim. It gives us 3. Right? Now we can also specify the type of data we want in our numpy array. So here I'm providing a list 1, 2, 3, 4, 5 to the array function, and I'm specifying I want floating type values in my numpy array. Let's see what it returns. It returns a numpy array with floating point values, right? And we can check the data type. So in this particular numpy array, we have floating values. So it has taken up all the integers and it has converted them into float because we have specified we want floating point values in our array. We can also convert them to integer as well. We can use np.array, and here I'm providing 5 floating point numbers in form of a list. And I'm specifying I want integer elements in my numpy array. Let's see what it returns. It returns 1, 2, 3, 4, 5. So what it is taking is it is rounding off all these integers to their lowest integer value. All these floating values into a lowest integer value. So 1.5 has been rounded off to 1, 2.6, 2, 3.1, 3, 4.8, 4, and 5.2, 5. This is taking the floor value of all these floating point variables. Again, we can check the type of this as well. Now it gives int 64 because the elements in this particular numpy array are integers. Now let's discuss about the different typecasting techniques. So here I have a numpy array which I'm generating using this integer list. Let's generate this array. Okay. Now we can use as type function to convert the elements in our numpy array into a different type. Here we had integer elements. I want float elements. So what I'll do is a.as type, which is as type, and I'm specifying I want floating point values. So it will convert all the integer values into float. We can see here for array 1 point, 2 point, 3 point, 4 point, and 5 point is added into the numpy array. We can convert it back to integer as well using the same process. And we can convert them into string as well. Let's check that. So here my array is holding string values. All of these integer values are converted into string. Let's check the type of this as well. A.e type. Which gives us U21, which is string type data. Now, let's see how we can create ND arrays by specifying a certain range. So we have this function arrange, which we have already seen while comparing list and numpy arrays. So we can provide the starting and the end of the range, and this arrange function will arrange the numpy array over that. Let's see. So This arrange function has taken the start value, which is 0. It has taken the end value, that is 10, and it is generating elements from these value. It will generate elements till end minus 1, which are 0 to 9, right? And by default, it has taken an interval of one element or one step at a time. It is going from 0 to 1, 2, 3, 4, and so on. Now let's see how we can specify the step as well. This is the third parameter, and here I'm specifying that my next element will be current element plus 2. So I'm initializing my array with 0. My first element is 0. Next element should be 2. Third element should be 4, and so on. Let's see what it represents. Yeah. So it has returned a NumPy array where we have a step of 2. Every element has a difference of 2 from the previous one, right? And it will go till 21, right? We need not even provide the starting point. By default, it will start from 0. So we can just run this, and it will also give us the same results as we saw here. So by default, it will start from 0. If we just provide one parameter, it will take it as the endpoint or end range. Now let's see how we can create ND arrays of ones. Ones means all the elements of these arrays will be 1. So we can just provide the dimensions of our array to this function ones, and it will generate the array of ones. If I give np.ones 5 and 5 comma 5, it will return a matrix of 5 into 5 size, and all the elements in that matrix will be 1, as we can see here. And by default, the data type is also float. Now we can also generate a 3D array of ones like this, and it has generated a 3D array now, right? So we can give a specific range and it will generate that array. Let's see if we just provide one dimensional data to it. np.ones. Let's say I just provided 10. So it has generated a one dimensional array of ones, right? We can also specify the type of data we want in our array of ones. So we can provide d type is equal to int, and it will generate integer type values in our NumPy array, right? Similarly, we can also create ND arrays of zeros using zeros function. And similar to what we did with ones, we can provide the range and the d type, and it will generate that array. Let's just run this cell as well. We got a 3 by 4 matrix of zeros, right? Now let's see how we can create ND array of specific value. Here we are creating array of zeros. Here we are creating arrays of ones. Let's see how we can create an array where all the values will be the value that we provide. So we can use np.full function, and this full function will take the range and the fill value as the input, and it will generate the array of these dimensions. So here I'm specifying 4 comma 5, which means 4 by 5. I want an array with 4 rows and 5 columns, and all the values should be 6. Let's just run this. It has generated the array as per the expectation. We can also generate an identity matrix of any size we want. Here I'm specifying 5. np.I will generate the identity matrix. And if we run this, it has generated 5 into 5 identity matrix, where the diagonals will be ones and rest of the elements will be 0. Right? So let's have a recap of what we have covered so far. We discussed about different ways of creating ND arrays, right? Then we discussed about the typecasting of ND arrays. We can just convert the type of our data using as type function. Then we discussed how we can create ND arrays using a specific range, right? Then we saw two important functions, that is np.ones and np.zeros, which creates n-dimensional arrays of ones and zeros respectively. Then we talked about np.full function, which will take range and the value as input, and it will generate a numpy array of that particular value with the given dimensions, right? Finally, we discussed about np.I function, which will take a variable n as input and it will generate n by n matrix of identity type, right? If I provide 3 here, it will generate 3 by 3 matrix, identity matrix, as we can see here. Diagonal elements are ones and remaining elements are 0. Now, let's see the different operations we can perform over our NumPy arrays. First of all, let's initialize a NumPy array 1, 2, 3, 4, 5, 6. I'm providing this list to array function and this will generate a NumPy array. Now, let's say I want to add 3 to all the elements in this particular list. How shall we do it with list? So I'll have to go to each and every element for element in list and I'm doing element plus 3, right? I'm storing it to a new list, L2, and this will give me a new list where all the elements of the initial list are added by 3. Let's see how we can achieve this with NumPy. In NumPy, I can just simply write a1 plus 3 and it will add all the elements with 3. Let's see. As we can see here, both the outputs are same, but here with very less coding, we were able to achieve the same results. Now let's understand how this works. So our initial array was this, right? We have this array. Now what NumPy is doing is, we have given an integer here. Integer is 3. It is generating a list with equal number of items from the initial list. So our A1 list has 6 items, right? 6 elements. It will generate a list of 6 elements where all of them will be 3. So 3, 3, 3, 3, 3. Yeah. Now what it will do is, it will add up the elements based on the indexes. So at index 0 in the initial list we have 1 and in the new list we have 3, right? So 1 plus 3 will be 4, 2 plus 3 will be 5, 3 plus 3 will be 6. This is how it will perform the addition operation. Now I need not even provide an integer. I can provide another NumPy array as well. So let's initialize this array. I can just do a1 plus a2 and it will add all the elements for these two NumPy arrays based on the indexes. So a1 plus a2 will give us the addition of both the list, both the NumPy arrays. Again, we don't even need to provide a NumPy array. We can just provide a list as well, and it will directly convert that list into NumPy array and add the elements based on the indexes. Here we can see 1 plus 2 will give us 3, 2 plus 3 will be 5, and this operation is also performed. Now, same as we did with addition, we can also do multiplication. We can just do this, and it multiplied all the elements by 2 in the initial array. Similarly, I can do subtraction as well. Let's see. I want to subtract by 3, so I should get the initial array, right? Okay, I need to store the result of this one. So let's say this is a temporary array We run this. And from that temp, let's remove 3. Yeah. So we got 1, 2, 3, 4, 5, 6, which is our initial array. Now let's see what our array holds. In A1, we have values from 1 to 6. In A2, we have values from 4 to 9. Let's multiply these two arrays. So A1 asterisk A2 will multiply all the elements of these arrays based on their indexes. So 1 into 4 will give us 4, 5 into 2 will give us 10, 6 into 3, 18, and all the elements are multiplied between these two arrays. Now let's perform the division operation. Here I'm providing a list of integers 2, 4, 6, 8, 10 to the array function. It will convert it into a numpy array, and then I'm dividing the resultant array by 2. So I got 1, 2, 3, 4, 5. But one thing we can see here is these are floating numbers, right? These are not integers. Why this happened is we are performing the division operation. So it has converted the integers into floats. We can also perform the integer division, which is this one. So we can just do double forward slash, and this will do the integer division. Here, the resultant values are converted into integers. We can also do the remainder operation. So it will divide all the elements by 3 and it will give us the remainder. So 2 by 3, we got 2. 4 by 3, we got 1. And 6 by 3, we got 0 because 6 is divisible by 3. So remainder will be 0. Right? We can also do the power operation. So by doing A1 double asterisk 2, it means all the elements will be squared from their current value. So 2, 4, 6, 8, 10, all of them will be squared and will get the squared values in the resultant array. So 2 square will be 4, 4 square will be 16, 6 square will be 36, and so on. Right? And we need not even provide just a single value. We can have multiple values as power as well. We can provide a list of powers. So my A1 array is a list of integers, and I'm doing the powers based on this new list, which is A2, and it is having the power values 2, 3, 4, 5, 6. So the resultant will have the first element of A1 will have power of 2, which is the first element of A2, right? And second element of A1 will have power of 3. Let's see what it returns. So as we can see, 2 to the power 2 will give us 4. 4 to the power 3 will give us 64. And 10 to the power 6 is giving us this value, right? So we can provide list of powers as well. We can also perform this operation where I'm dividing 2 by all the elements in a certain numpy array. Let's see what it returns. So 2 is divided by 2, we got 1, right? Now 2 is divided by 4, we got 0.5. 2 is divided by 6, we got 0.33. This is how we can also perform division operation over an integer from a given numpy array. Now another great example of numpy outshining the list is, let's say this is the list I have, and I want to check what all elements are smaller than 4, and I want to get those elements. If I run this code, this will throw an error because this operation is not allowed in list. What I'll have to do is I'll have to go to each and every element using a loop, and then I'll have to check if that is less than 4, and then I can see the results. But in NumPy, we can just do this operation where A1 smaller than 4 and it will return a NumPy array like this. So this NumPy array has true and false values. What does true and false value represents? So if the given integer is less than 4, 1 is less than 4, right? So it gives true. Wherever the condition will be true, it will return a true, otherwise it will return a false, right? So 1 is less than 4, we got 2. 2 is less than 4, we got true. 3 is less than 4, we got true. And rest of the elements are either equal to 4 or greater than 4, so we got false. Now let's see how we can compare different NumPy arrays. So let's first do the same thing with list. I have these two lists and I want to compare each and every element of these two lists and see which one has higher number of greater elements. So let's see what this code will represent. It is checking if L1 is smaller than L2 and it returns false. So in list, what happens is it will go from the first element. It checks 9 is smaller than 7. The condition is false. So here itself, it will return a false. It won't compare the remaining elements. But when we do the same operation with NumPy, let's say these are the two lists I want to compare. Let's initialize them. And then we are doing this operation. A1 smaller than A2. It returns true, true, false, false, true, true. Let's validate. 2 is smaller than 3. Yes. So it returns true. 1 is smaller than 4. This is also true. 4 is smaller than 2. This is false. Hence, this is returning false. 5 is also not smaller than 1. So we have false. This is how we can compare two NumPy arrays. You can also check which one is greater by doing this. A1 greater than A2 will compare all the elements based on the indexes and then it will return the Boolean values based on the condition being true or false. Now we can also do smaller than equal to and greater than equal to operation, and these will also do the index wise comparison of elements and return the Boolean arrays, right? Now let's check what A1 equal A2 does. It returns false in all cases because at a given index, no two elements are same in my array. Let's say I had 6 here instead of 7. Now let's check this A1 equal A2. For the last element, it returns true now because 6 is equal to 6 and they are both in the same index. So one important checkpoint that we need to keep in mind is operations between two ND arrays is not possible if shapes are not the same. So if I have one NumPy array as 1, 2, 3, 4, 5, which are 5 element, and another NumPy array with 6 elements, and I'm doing an addition operation here, then it will throw an error that the shapes are not the same for two given NumPy arrays, right? Now let's see the different indexing and slicing techniques over ND arrays. So let's first create a NumPy array using a range function. Now A of 0 will give us the first element of the NumPy array. So it's the same indexing that we used to do with strings and list. A of 0 will refer to the first element. A of 1 will refer to the second element in the NumPy array, which is 1. A of 6 will refer to the seventh element because the indexing is from 0, right? Here A of -1 will refer to the last element. This is reverse indexing, right? -1 will refer to the last element. -2 will refer to the second last element. So this will be 8. Now A of 0 colon 8. Here what we are doing is we are slicing from the 0th index till 8 minus 1. So this is end index and we'll go till end index -1. So we'll get all the elements from 0 to 7, right? Let's check. Yeah, so we got all the elements from 0 to 7. If we specify nothing with the columns, So let's just check what this represents. This will give the entire array because no starting or ending index is given. Let's say I want to go up till index 8 and I want to skip two indexes. So I'll get the alternate elements. I'll start from 0. I'll start from 0. I'll go to 2. Then I'll go to 4. Then 6. Right? This is how we can slice elements from our NumPy array. We can also do something like this where I'm going from -8 till -3. Now where does -8 fit in my array? So let's first have the array here itself. So -8 will go from the last. -1, -2, -3, -4, -5, -6, -7, and -8. Right? So -8 refers to this element. Right? And -3 refers to -1, -2, -3. -3 refers to 7 and will go one step lower, right? We'll go to end -1. So this will be 6. So we'll get 2, 3, 4, 5, 6 as the output. And we can also get the reverse of our ND array if I just doing this. So by default, if you provide step as -1, it will start from the last element and reverse the array like this. We can also specify that we need to start from the last element, and let's say we only want to go till 2. Let's see what this will do. So what it is doing is at index 2 we have 0, 1, 2. We have 2, right? And at index -1 we have 9. So we'll start from 9. We'll go up till 3, right? We can also skip the steps with -2. So it will start from 9, then 7, then 5, then 3. This is how we can perform slicing over ND arrays. This is quite similar to what we have seen with list and strings. Now let's see how we can reshape and transpose our NumPy arrays. So let's arrange a NumPy array. np.arrange 16, which will arrange numbers from 0 to 15. Let's check the shape. Let's check the dimensions as well. It is one-dimensional array. Now let's say I want to reshape this particular NumPy array with this dimension 16, 1. Let's see what it gives. So what it has done is it has transposed our entire array into a single column, right? We have 16 rows and one column. Previously we had one row and 16 columns, right? Now we can check the shape and it is 16, 1, right? We can check the dimensions as well. Now this is a two-dimensional array because it has more than one row, although there is a single column, right? Now let's reshape it again 1, 16. So I want one row and 16 columns. We are back with the initial array again, right? You can check the shape. So it is 1, 16 now. One row, 16 columns. A.ndim will give us the dimension is still a 2D array because we have specified that we want 1, 16. Previously, it only had one dimension, but now it has been transformed into a two-dimensional array, even though it represents a single dimension of data. A.reshape. Now let's understand what reshape function will do in this case. We are providing 4 by 4. In total, we had 16 elements, right? So any multiple of these will be fine for transforming our array. I want to reshape to 4 by 4. So what it will do is it will create a matrix of 4 into 4. Let's see. So we have the matrix where all the numbers are aligned like this. 0, 1, 2, 3 are in the first row, 4, 5, 6, 7 are in the second row, and so on. Now let's reshape it again. But now I want a three-dimensional matrix. So I'll provide 2, 2, 4. This will be 2 into 2 into 4. So we'll get a 3D matrix like this. So now let's check the total number of shapes we can have for our ND array. My current array, let's say I initialize the array as np.arrange 36, and then I'm reshaping it multiple times, right? I first reshaped it to 1, 36, then 2, 18, 3, 12, 4, 9, 6, 6, 9, 4, 12, 3, 18, 2, and 36, 2, right? So these are the possible 2D shapes for my NumPy array when we create NumPy array with this integer, right? We can also use these two functions together. So np.arrange will arrange a NumPy array of 16 elements from 0 to 15, and then we'll reshape it to 4, 4 or 4 into 4 matrix. So it will return a matrix directly. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13, 14, 15, right? This is how we can reshape our NumPy array. And if we do a dot t, it will transpose our NumPy array. So our rows will become the columns and columns will become the rows. Let's see. So here my initial array was 0, 1, 2, 3. Now I have 0, 1, 2, 3 in the first column. Then I have 4, 5, 6, 7 in the second column, 8, 9, 10, 11 in the third column, and 12, 13, 14, 15 in the last column. So this is the transpose operation. So let's have a recap of what we have covered so far. So we have talked about the operations on our ND array, right? How we can add, subtract, multiply, divide. We can also use special operations like integer division, remainder, power, all these operations directly on all the elements in a NumPy array. We can also perform addition, subtraction, and all these calculations over multiple NumPy array as well, as we can see here. We can also do comparisons between NumPy arrays by directly providing the operators and compare them, right? The only catch is we cannot compare, we cannot do operations between two NumPy arrays of different shapes, right? Then we saw how we can do indexing and slicing over our ND arrays. Similar to how we did with list, we can perform forward or reverse slicing and indexing over our NumPy arrays as well. Then we saw how we can reshape and transpose our NumPy array. We can use the reshape function and we can provide the specific range we want to or specific format we want for our array. Right? If we provide 4 by 4, it will be creating a 4 into 4 matrix of our data. Right? Then we saw a dot t, which will transpose our array. With that, we can conclude our first session on NumPy. Let's talk about the key takeaways or summary of this session. So we first talked about n-dimensional arrays. We talked about what n-dimensional arrays are. Then we tried to compare NumPy with list, and we saw how NumPy can perform the same task that we can perform with list, but in a much more efficient manner. Then we talked about different ways of creating NumPy arrays. We also talked about the operations that we can do over n-dimensional arrays. Then we talked about indexing and slicing over n-dimensional arrays. And finally, we talked about how we can reshape and transpose our NumPy arrays. That will be all for our first session on NumPy. In the next session, we'll talk about some more advanced topics related to NumPy. If you like this video, please provide the feedback for this video. That will definitely help us to improve the quality of our lectures. Thank you for joining this session. All the best for your preparation. Happy learning.